Swagatam, welcome back to my Get Really lecture series, learning, learning something, seeing the beautiful sights of Indian village. I am Get Handler and I am teaching you some important point related to the physics. And in this lecture, in the previous lecture, we talk about SHM and some topic related to SHM. First, so before starting, I like to tell Jai Sri Ram, Sita Ram, Sita Ram, Sita Ram, Jai Sri Ram, Jai Hanuman Ji, Jai Hanuman Ji, Jai Bajrang Jai Bajrang And also I want to inform you that the Bajrang have given me blessing, and now I have got job in my own country with a hike of 800 times in my salary. So only today I will give you 2 and 3 lectures, and after that what the owner of FFBMD channel will proceed this lecture. I am very thankful to all people of India or Bharat or villager peoples of India and Bharat. They help me, they liked me, they always help me in doing work here. They are good, they are full of kindness, they are smart. These villager peoples are very nice. They always help me. They afford me milk and food free of cost. They always help me. I am fully obliged to these peoples of this village. So let's start now my topic. In the previous lecture, we learned about the laws of vibrating stress testing, that is, in this case, the fundamental frequency of a stress testing is given by nu equals to 1 by 12 into under root T by mu. From this we get the law of length as V nu proportional to 1 by L when temperature and mu are constants. Mu means reduced mass, and law of tension nu proportional to under root T when length and reduced mass are constant, and law of mass is given as nu proportional to 1 by root mu when length and tension are constant. Again, we know that if rho is the density of the material of the string and d is the diameter of the string, then mass per unit length is given by mu equals to pi into d square into rho by 4. So the frequency becomes 1 by the fundamental frequency becomes 1 by 12 into under root 4 into T divided by pi into d square into rho, or equals to 1 by L into d into under root T by pi into rho. And laws of vibration of stress strings can be verified experimentally by using a sonometer. Sonometer is a device which, with which we can verify these laws. Now, in the discussion, we will talk about the closed organ pipe. The pipe whose one end is closed and other end is open is called closed organ pipe. In a closed organ pipe, the closed end is always a node while the open end is always an antinode. Now the fundamental mode or first mode lambda is equals to 4L, where L is the length of the pipe, hence fundamental frequency nu1 equals to V by lambda 1 equals to V by 4L, 4 into L, where V is the speed of sound in air. This frequency is called first frequency. For second mode, in this case, two node and two antinode will be formed, and wavelength for second mode will be given as 4L by 3. So frequency nu2 equals to V by lambda 2 equals to 3 into V by 4 into L equals to 3 into 3 nu1. And this frequency is called third harmonic or first overtone. Similarly, the third mode lambda 3 equals to 4L by 5, because in this case 3 antinode and 2 node is formed. Three antinode and 3 node is formed. So lambda 3 will be equals to 4L by 5, hence frequency nu3 equals to V by lambda 3 equals to 5 V by 4L equals to 5 nu1. This frequency is called fifth harmonic or second overtone. 9 nu1 is to nu2 is to nu3 equals to 1 is to 3 is to 5. Only odd harmonics are present. Similarly, for nth mode, lambda n equals to 4 into L by 2n minus 1, and frequency nu n equals to V by lambda n equals to V into in bracket 2n minus 1 by 4 into L equals to in bracket 2n minus 1 into nu1, where n equals to 1, 2, 3, dash, dash, dash. This frequency is called 2n minus 1th harmonic or n minus 1th overtone. Now let's talk about open organ pipe. The pipe in which both ends are open is known as open organ pipe. In an open organ pipe at both ends there will be antinodes. Now if the length of the pipe is L, then for fundamental mode or first mode, lambda 1 equals to 2L, because in this case 2 antinode and 1 node is formed. because both end have antinode and in between there is a node, and L is the length of the pipe. Hence for first mode lambda 1 equals to 2L. Now fundamental frequency nu 1 equals to V by lambda 1 equals to V by 2L, where V is the speed of sound in air. This frequency is called first harmonic. Now for second mode lambda 2 equals to L, and in this case 3 antinode and 2 node will be formed. So frequency nu t equals to V by lambda 2 equals to 2 nu 1, and this frequency is called second harmonic or first overtone. Again for third mode lambda 3 equals to 2L by 3, and in this case 4 antinodes and 3 nodes are formed. So frequency nu 3 equals to V by lambda 3, or nu 3 equals to 3 into V by 2L equals to 3 nu 1. This frequency is called third harmonic or second overtone. Now taking ratio, we get nu 1 is to nu 2 is to nu 3 equals to 1 is to 2 is to 3. Hence in open organ pipe all harmonics are present, whereas in a closed organ pipe only odd harmonics are present. So this is the difference between harmonics present in open and closed organ pipe. You have to keep in mind that in open organic pipe all harmonics are present, but in closed organ pipe only odd harmonics are present. Now again for nth mode in the open harmonic open organ pipe, the nth mode will be given for nth mode lambda n equals to 2L by n. So frequency nu n equals to V by lambda n equals to n into V by 2L equals to n into nu 1, where n equals to 1, 2, 3, dash, 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 dash. And this frequency is called nth harmonic or n minus 1th overtone. The fundamental frequency of an open organ pipe is twice that of a closed organ pipe of the same length. If an open pipe of length L is half submerged in water, it will become a closed pipe of length half that of open pipe. So that of open pipe, so its frequency will become nu c equals to nu y 4 into L by 2 equals to nu y 2L equals to nu O, that is equal to that of open pipe, that is frequency will remain unchanged. Now the next point is about end correction. Now let's talk about end correction. The antinode at the open end of a pipe is not formed exactly at the open end but a little outside. This is called the end correction. This is denoted by a small e and is given by e equals to 0.6 r, where r is the radius of the pipe. If cap L, that is capital L, is the length of pipe, then for closed organ pipe L is replaced by L plus E, while for open organ pipe L is replaced by L plus 2E. Now due to end correction, the fundamental frequency of a closed organ pipe is nu C equals to, C is used for closed, equals to V by 4 into under bracket L plus E in bracket L plus E equals to V by 4 into in bracket L plus 0.6 R. Due to the end correction, the fundamental frequency of an open organ pipe is given by nu O for open equals to V by 2 into open bracket L plus 2E close bracket equals to nu by 2 into open bracket L plus 1.2 into R close bracket. Now let's talk about the speed of sounds in air by resonance tube. A speed of sound in air at room temperature by using resonance tube is given by nu equals to 2 into 2 nu into in bracket L2 minus L1, where nu equals to frequency of the tuning fork, L1 equals to first resonance length and L2 equals to second resonance length. And in this case, end correction is given by E equals to L2 minus 3L1 by 2. Now the next point is about beats. When two waves of nearly equal but not exactly equal frequencies traveling with same speed in the same direction superpose on each other, they give rise to beats. Beat frequency. Now it is defined as number of beats heard per second, and beat frequency is equals to number of beats divided by second equals to nu1 minus nu2 equals to difference in frequencies. So beat frequency equals to difference in frequencies. Phenomenon of beats can be used to determine the frequency of a tuning fork. Consider if nu A is the known frequency of a tuning fork A and nu B is the unknown frequency of tuning fork B. When both tuning forks A and B are sounded together and produced bits of frequency nu, then nu B equals to nu A plus minus nu. Here plus minus sign of nu is decided either by loading or by filing any one of the tuning forks. If the tuning fork B is loaded with wax and sounded with the tuning fork A, if the bit frequency increases, then nu B equals to nu A minus nu. If bit frequency decreases, then nu B equals to nu A plus nu. If instead of loading the tuning fork B with wax, tuning fork B is filed and sounded with the tuning fork A, if the bit frequency increases, then nu B equals to nu A plus nu. If the bit frequency decreases, then nu e equals to nu a minus nu. Loading a tuning fork with wax decreases its frequency, while filing a tuning fork increases its frequency. Tuning fork is a source of sound of single frequency, and frequency of a tuning fork of arm length L and thickness D in the direction of vibration is given by nu equals to d by L square into nu equals to d by L square under root y by rho, because V equals to under root y by rho, where y is the Young's modulus and rho is the density of the material of the tuning fork. Now let's talk about the Doppler's effect. When a source of sound or an observer or both are in relative motion, there is an apparent change in the frequency of sound as heard by the observer. This phenomenon is called Doppler's effect. Now, according to Doppler's effect, the apparent frequency heard by the observer is given by nu dash equals to nu into, in the bracket, nu v plus minus v naught divided by v minus plus vs, where vs, v0, v naught or v0 and v are the speed of source, observer and sound relative to ear. That is, vs represent velocity of source, v0 represent or v naught represent velocity of observer, and v represent the velocity of sound relative to air. The upper sign on vs or v naught is used when source or observer moves towards the observer or source, while lower sign is used when it moves away. Next point, if the wind blows with Vw in the direction of sound, then V is replaced by V plus Vw in the above equation. And if the wind blows with a speed Vw in a direction opposite to that of sound, V is replaced by V minus Vw in the above equation. If source and observer both are stationary, that is, Vs equals to V naught equals to 0, then V dash equals to V. Nu dash equals to nu, not V. Nu dash, that is frequency. Similarly, if source and observer both are moving in the same direction with same speed, that is, Vs equals to Vo, then nu dash is equal to nu. Thus it is clear that if there is no relative motion between the source and the observer, then there is no Doppler effect. When a source is revolving in a circle and observer is stationary outside, the following situation comes. Now the next point, characteristics of a musical sound. A musical sound has the following three characteristics: loudness, pitch, quality or timbre. Loudness is a subjective sensation which is determined by the intensity of sound and by sensitivity of the observer's ear, and it depends on the listener. Next, the loudness of a sound of intensity I is given by L equals to, capital L is used for loudness, L equals to log I by I naught, log to the base 10. Here we take log to the base 10, where I naught threshold intensity, which is equal to the 10 to the power minus 12 watt per meter square. And a practical and a small unit of loudness of sound is decibel, represented by dB, a small d and capital B together, and 1 decibel equals to 1 by 10 bell. In decibel, the loudness of sound of intensity is given by L equals to 10 into log I by I naught. Here log is to the base 10. Now pitch. It determines the sharpness or shrillness of sound. Higher the frequency, higher is the pitch, and hence sharper is the sound. Next is quality. It is that characteristics of a musical sound which differentiates sounds coming from different sources even when they are of same intensity and same pitch. Now let's talk about reverberation time. Reverberation is the phenomenon of persistence of sound for some time after the source stops producing sound. The time for which sound continues to be heard after the source has stopped producing sound is called reverberation time. According to Sabin's formula, the reverberation time of a hall is given by T equals to 0.16 into V by sigma A subscript I into S subscript I, where V is the volume of the hall in meter cube and sigma A subscript I into S subscript I equals to A1 S1 plus A2 S2 plus A3 S3 plus dash 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 equals to total absorption of the hall, where S1, S2, S3 are the area of surfaces in meter square which absorb sound, and A1, A2, A3 dash 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 are their respective absorption constant. So with this, I would like to end this lecture, but before ending this lecture, I would like to tell you that I am very happy because I am going back to my own country, and I am very much grateful to Bajrang Bali, who helped me in getting job in my country. Jai Sitaram, Jai Sitaram, Jai Sitaram, Jai Hanuman, Jai Bajrang Bali. Om Namah Shivaya, Om Namah Shivaya, Om Namah Shivaya.